Hello and welcome to my presentation about the role of fracture in the reduction of iron ore with hydrogen. This is a collaborative effort of a big team, and I will highlight the individual contributions of all the team members as we go along through the lecture. We currently produce the sheer incredible amount of about 2 billion tons of metallic products every year. By far the biggest contribution, of course, comes from iron, but we also have gigantic amounts of aluminum, nickel, copper, or even platinum, to name but a few other metals. This enormous success of metallurgical products comes, of course, with a huge burden. This is, for instance, the fact that the production of metals consumes about 8% of the global energy per year. And what is even more staggering is that this metallurgical production also consumes about 30% of all industrial greenhouse gas emissions per year. So this is by far the biggest single contribution. On the other hand, we of course have all the wonderful and important products we lean on, and we should also recall that the global market for materials is about 3,000 billion euros per year, which is a gigantic market which depends on metallurgical products. And the question now is whether this market can be turned into a circular, into a sustainable market. And the next step is, of course, what in this setting the contributions from basic material science and metallurgical research could be. And this is essentially the context of this presentation. There are, of course, many aspects that we can tackle by basic and applied research. This is a diagram which shows the technology readiness against the scaled potential for impact. So it shows us how close certain techniques are to applications and how big their impact might be. The biggest impact, of course, with the highest readiness is corrosion protection and improving materials longevity. A likewise very high impact comes from using more electrical energy resources when making metallurgical products, provided they come from renewable energy sources and not from carbon-based energy supply. There are, of course, many other aspects, such as producing less scrap or better byproduct management, producing and wasting less of the often poisonous byproducts from metallurgical production. But when it comes to aspects that have a very high impact and at the same time are still quite far away from application, you see, we have to deal with the CO2 reduced production of metallurgical products. And this is also the deeper context of this presentation, focusing here particularly on iron. Why do we focus on iron? Because when you take a look at coke plants and the classical blast furnace production route, then you can appreciate that about 6% of the global CO2 emissions are created by these two production steps. That means the impact of these specific technologies is really gigantic, and that's why we draw our attention to them. And make no mistake, the growth of the steel market is still gigantic. You don't see it everywhere, but believe me, steel is everywhere around you, and still the growth rates are staggering. We currently produce about this year 1.8 billion tons of steels, and this is forecast to grow towards the year 2050 to the gigantic amount of 2.8 billion tons of steels. So this is simply gigantic and is creating a gigantic wave of CO2 problems related to global warming. That means it's a very urgent and pressing burden to deal with that problem. There are many ways how you can produce raw iron from its ores. This is just a little overview, and I will by no means go through all of these techniques. This is just for reminding you that we have quite a variety on the left-hand side shown, where you can reduce the iron ores by carbon carriers. This can be coke or can be natural gas, and you can do it through a liquid phase or you can do it through a solid state phase. That is then called direct reduction. And the classical route is of course a liquid phase route, where the reduction takes place in the solid state, but then you tap the liquid iron in its near eutectic state, and that is the so-called blast furnace route. There are of course also viable alternatives where you directly use electrical energy, such as in iron electrolysis, which is also a very promising avenue. In this presentation and investigation here, we deal particularly with the so-called direct reduction technique, which is based on the direct and solid state reduction of iron ores by using hydrogen, such as shown here. And the iron sponge that you produce thereby would then later enter, for instance, into an electric arc furnace. And we now take a little journey through the microstructure of these pellets, which are pelletized products of the original iron ores. And we start with hematite, so Fe2O3 as a starting product. And we conduct this reduction analysis at 700 degrees centigrade, and we use pure hydrogen for this. This diagram shows the mass change as a function of time. And here you have the temperature range. That means we keep the temperature constant at 700 degrees centigrade and follow the mass loss as a function of time to track the reduction. When you look at the corresponding derivatives, then you can see that the reduction rate, which is plotted here on this axis, changes as a function of the reduction degree. This is a very important diagram because it shows you where the kinetics in the reduction is fast and where it is slow. And we see that particularly at the beginning, the reduction is very fast when you reduce the hematite into the next oxidized states, which is the spinel, namely the magnetite, Fe3O4. And the by far slowest and longest reduction takes place in the transition of this magnetite at 700 degrees centigrade into the wüstite, and further from the wüstite into the iron, of course. So the kinetic bottleneck is, so to say, the reduction of the wüstite, which makes this process really slow. The theoretical picture behind this reaction is shown in this diagram. You have here the last stage of the overall reduction sequence, which is the wüstite, the FeO, such as shown here. And as you reduce in the beginning that material through a surface reaction between hydrogen and the oxygen, you form a layer of iron on top of the wüstite. And that means that due to the gradient and the chemical potential of the oxygen must leave the oxide and diffuse outbound towards the free surface or pore or surface of the pellet to react there with hydrogen to form water. And these are the different kinetic steps that have been considered and might act as individual bottleneck reactions for the overall kinetics. And it is a task to identify these bottleneck steps in the overall kinetics and find solutions to make them faster, to make this type of production route viable. Let us have a little fly through the wüstite pellet, to the hematite pellet. Originally the pellet is hematite. So we cut it through and you see a modest porosity which is inherited from the processing step. That was originally designed for classical direct reduction processes, because this is a so-called direct reduction pellet. And you see that this material has a very complex microstructure consisting not only of multiple pores but also of multiple interfaces, grain boundary, and internal free surfaces. When you look but a little bit closer at a higher resolution after some reduction state, and we look at this later in much more detail, then you can indeed see after a certain reduction time a very complex internal structure with inherited porosity, but also with newly acquired porosity, which is due to the mass loss. Let us look a little bit closer to this. You can put this now into full field simulations, the details of which will be subject to a separate lecture. This will not be discussed in this lecture. And then you can, based on this real microstructure of the pellet, do corresponding simulations how the reduction of the wüstite is progressing under such geometrical confinement conditions. So there's in principle a Ginzburg-Landau phase field simulation behind this. So what is really interesting is to take a little look into the partially reduced pellet. And this partially reduced pellet is shown here in terms of an SE image. SE stands for secondary electrons in the scanning electron microscope. And you again see this inherited porosity from the preceding pellet manufacturing steps. And this map shows from the EBSD measurement the phase distribution and the so-called IQ, which is the image quality, which tells you how many defects you would find into each of these phases. And you see here specifically after 1 minute exposure to pure hydrogen at 700 degrees centigrade, 2 phases. One being the original hematite, so that is the original material from which the pellet was made. And this is the already reduced material into magnetite. So this is the first reduction step, which, as we saw in the beginning, is a very fast reduction step. But you can see really how these 2 phases are really intermixed. So there's no global huge growth front that goes through the pellet from the outside to the center alone, but you have also inside each of these near surface or near center regions a very complex interplay of the geometry and the local reduction kinetics. Now let's look at this a little bit more in detail, because there are not only structure features, but there are also chemical features that you inherit. Because depending on where you get these ores from, you have also chemical heterogeneity in the material and not only structural heterogeneity. This is shown here from a micrograph in a BSE image from the initial iron ore pellet, and you see here in terms of the iron distribution that you have also other elements such as titanium, sodium, even vanadium, magnesium, and so on. So that means you will later see when we go to a near atomic scale analysis that these features also play a role in the reduction kinetics. Here you see again a pellet that has been reduced again by pure hydrogen at 700 degrees centigrade. So all the data are taken at 700 degrees centigrade. And then you see how some of these chemical features, of course, prevail over the reduction. And we later look at this, as I said, in more detail. The message of this diagram, of this picture, is just to remind us that we inherit complex structural features and complex chemical features when we deal with the understanding of the role of microstructure and internal fracture and internal kinetics on the overall hydrogen-based reduction. Here's now a somewhat more detailed analysis of a material that was reduced under pure hydrogen at 700 degrees centigrade for about 10 minutes. What you see here is a wide variety in the SE, secondary electron image, a wide variety of different features that we want to look at in more detail. When we take this first view at this region, then you see that you have a complex interplay of the ferrite and the newly formed porosity, which is due to the mass loss. So in the areas where you have adjacent wüstite to ferrite, you very often find these pores that newly open up, like here and here. What you also see, what is very interesting, when you see ferrite that is growing inside of the wüstite, this is a wüstite, this is a ferrite, you see very complex interfaces here from the wüstite to the ferrite, and again substantial porosity that you see everywhere building up between these 2 phases. And here you see even something like a delamination at the interface between the bright shining ferrite and the slightly darker wüstite. So, which is obvious because you have more than 40% weight loss between the wüstite and the ferrite. This is shown here in a higher resolution, again at the interface between ferrite, which grows on top of the wüstite, and here's the wüstite. Again, the bright face is the ferrite, and you see numerous types of pores and cracks that are building up here everywhere around that growing ferrite. The other thing is, and we look in a minute into this in detail, is at the direct interfaces. When you go to the ECI contrast, which stands for electron channeling contrast imaging, you build up also certain dislocation and defect populations everywhere inside of the wüstite. That is what you see here. That means we must, for interpreting the kinetics of the reduction, also consider the formation of internal defects both inside of the wüstite and ferrite. The reason for that is again that the volume mismatch between the two is very high and leads to substantial stresses and also to fracture. And this is also shown here again, where in the secondary electron image you see again ferrite forming in the wüstite, and here in the wüstite you see everywhere this very fine porosity which builds up. This is, by the way, also very important, because when hydrogen can diffuse to these open pores from the outside, then the outbound diffusing oxygen from the reaction interface can already recombine in these pores to form water, which is also a very kinetically important aspect. Let us zoom in a little bit on one of these areas by using EBSD, which stands for electron backscattering diffraction, and we investigate again the interface between the red plotted ferrite and the green plotted wüstite. And we take these three arrows of different length and plot them shown here and reveal the point to origin in terms of the misorientation coming from the outbound wüstite towards the ferrite interface, then you can see the substantial buildup of orientation gradients before these interfaces due to the high stresses that are building up. And of course, these gradients are translated to corresponding GNDs, where GND stands for geometrically necessary dislocations, and again these defects can play a role for the local kinetics. This is shown here in terms of beautiful in situ experiments by Professor Mark Willinger from the ETH in Zurich. Let me repeat the movie. Here you can nicely see when he exposes such a pellet directly inside the electron microscope to hydrogen, as is shown here, then you can see how this relatively smooth iron film really forms on top of the wüstite. That means you build up this certain barrier of iron through which both the hydrogen and the oxygen must diffuse. Now, what is also interesting to look at the development of the internal porosity as a function of the reduction time. This is shown here, and you have this inherited porosity that we have seen before in the pellet prior to the hydrogen-based reduction. And when you start reducing it, you see how the porosity that is shown here with about 27% in the beginning grows towards a value of more than 40%, which is then shows the difference of the acquired versus the inherited porosity. That means you have about 20% of the porosity is created during the reduction. And some of this is due to fracture, others are due to diffusive porosity growth. What is also very interesting, if you do not only look at the very fine scale, but take one step back and look at the gradients of the reduction kinetics and the porosity through the thickness of the pellet. When we show that here in terms of a pellet which has been cut through and follow these three positions from the outside towards the center, then you can see how the reduction is much higher in those regions which are closer to the outside, and it's much more sluggish in those regions which are closer to the inside. So this can be explained that in part the oxygen must obviously also take a long diffusive path outbound of the pellet, or at least towards the next available internal interfaces. And now we switch gears and go through a much finer scale, namely to atom probe analysis. And you see here a direct atomic scale resolved interface between the wüstite on the left-hand side and the alpha iron on the right-hand side. And you can very nicely see this very strong drop in the oxygen content as we have stipulated before, which explains how the wüstite must, through this chemical potential gradient, now diffuse outbound through the iron. What is also very important to see here, however, is this very high buildup of silicon, which is deposited on this moving interface, which would obviously make this motion of the interface during the last step of the reduction much more sluggish. So the take-home message from this picture is that we also have to consider the impurity drag, so to say, on that interfacial interface as a function of the reduction. Another point is that you also form other type of oxides. Here, for instance, we find also more complex oxides based, for instance, on sodium or also on magnesium. And these, as you know, have very high enthalpies with the oxygen, which is harder to reduce by hydrogen, so that some of these oxides prevail as the reduction goes ahead. And here's another picture that shows similar features with not only magnesium-rich oxides, but also titanium-rich oxides, which remain in the pellets during the reduction and can make the process more sluggish. So in future, it's also important to not just understand the microstructure, the evolution of fracture, internal damage, and porosity due to the mass loss from the wüstite and towards the iron, but also how these impurities affect the rate of the reduction. Last but not least, we should also emphasize that you must also understand how much hydrogen really remains inside of the material. Because when we have iron that is produced with a too high hydrogen content, due to this type of reduction, you might later encounter the so-called hydrogen embrittlement in your materials, which you of course do not want. This is shown in this type of curve. And these curves are often published in the literature, which simply show that when you expose a material to high content of hydrogen charging, then you get the so-called hydrogen embrittlement, which becomes visible in a reduced tensile ductility. And it is of course also the target to better understand pore formation due to hydrogen in the solid state iron and decohesion, which both are mechanisms that contribute to the hydrogen enhanced damage. And the task is here, like said before, that we also want to study these effects in the freshly produced iron due to hydrogen in the as reduced state down to the atomic scale and with theoretical understanding. This is just a projection of what kind of research has to come here in the future. With that, I thank you very much for your kind attention and for attending this online talk. And if you want to have a broader view on this topic, there are movies on YouTube related to the field of sustainable metallurgy. And I thank you again very much for your attendance.